Alright guys, so we talked about the three steps of forming a solution, or what happens at least on a thermodynamic levels of forming a solution. So the first and second step kind of go hand in hand, where we're separating the solvent and the solute to allow room for the two to mix together. Remember, both of these processes require the breaking of intermolecular forces and therefore have a positive delta H, or positive enthalpy, meaning it's endothermic. And then the last step is where they come together and they actually form intermolecular forces between them. And remember, forming intermolecular forces is exothermic, or a negative delta H. Okay? So let's keep kind of looking at this. So these three steps together will give us the delta H of the system. So when we get to enthalpy and entropy and Gibbs free energy and thermochem a little bit later on in the next unit, we'll talk about the fact that the system is the combination of all the steps put together, which should make a little bit of sense. If you're traveling to, let's say, Target, and then you travel to Panera for lunch, and then you travel to Kroger to get something else, the combination of all three of those steps is the full distance or time, or however you want to think about it, that you were out and about and traveling. So when we talk about the enthalpy of solution, we're talking about the energy of step 1, 2, and 3 all being put together. So again, remember, step 1 and 2 are breaking intermolecular forces of the solute and solvent. Step 3 is the formation of intermolecular forces between the solute and solvent, and all three together give us the delta H of the solution. Okay, so what we need to understand as we move into thermodynamics, there is an equation which is called Gibbs free energy. Delta G equals delta H minus T delta S. Now, we're not going to play with this too much right now, but what I want you to understand is delta G determines what we call the spontaneity of the reaction. And spontaneity, or spontaneousness, really just means that it's going to occur on its own, or without any intervention. So again, we're going to get to that a little bit later. What we need to understand is that we always want delta G to be negative for something to be spontaneous, or for it to occur. In this case, as we are looking at the formation of a solution, delta S is something we call chaos, or entropy. And that's always going to be positive for a solution, because we're taking two separate things and mixing them together, and automatically when you mix something, you automatically get positive. Okay, which means this statement right here, negative T delta S, is negative. Okay, where I'm getting that negative is this negative right here I'm distributing to this T delta S statement. So it's like adding a negative here. Okay, if that makes any sense kind of mathematically. And again, this will make a little bit more sense as we move on. I'm just kind of giving a little bit of background here. So delta H, what we want to see in terms of a solution, for a solution to form spontaneously, and again, I'm using that term as kind of a precursor for the next chapter, but spontaneous just means it's going to occur on its own, which really in terms of solution means that the solute is soluble and will dissolve readily. What we want for delta H is for it to also be negative, so that we have a negative plus a negative is going to give us a negative, and delta G, if it's negative, makes it spontaneous. We can also have a small positive delta H, so we want either a negative delta H or a small positive delta H. And the reason I'm saying a small positive delta H is if I add a small positive with a large enough negative, they will add up to still give us a negative. It may be a small negative, but a negative delta G is a negative delta G, which means it's spontaneous regardless of its size. So that's kind of what we're looking for here. So let's kind of look at this and see if we can determine why some solutions will form, meaning the solute is soluble, and why some solutions will not form, the solute is insoluble. Okay, so let's first talk about oil and water. If I put oil and water, will they mix together? Will they dissolve into each other? Will the oil dissolve into the water, or the water dissolve into the oil? Answer is no. We know that just from a manner of everything we do in everyday life. Okay, so let's kind of talk about why. First off, step 1 is to either break the solute or the solvent. Okay, I'm going to break the solute, which I'm going to make oil. Okay, well, breaking oil, breaking intermolecular forces of oil, is breaking LDFs. Okay, well, are LDFs strong or weak? Okay, they're weak, which means we have a positive delta H, and it's going to be a fairly small delta H for this first step, and the reason being is because we are breaking weak intermolecular forces. So small positive delta H. It requires energy. It's always going to be endothermic because we're breaking into molecular forces, but it's a small intermolecular force, or a weak intermolecular force, so not a lot of energy is required. Okay, step 2 is breaking the water, breaking the intermolecular forces of water, which of course we know are hydrogen bonds, which we know those to be strong. Okay, well, that means we're going to have a larger positive delta H. So again, going to require energy. Both these steps are going to be positive endothermic. One's going to require a little bit of energy because we have weak intermolecular forces. One's going to require a little bit more energy because we have strong intermolecular forces. And then step 3 is putting them together. Okay, so we are forming an intermolecular force between the oil and water. Okay, well, what type of intermolecular force is going to form between oil and water? Let's go back and kind of talk about our intermolecular forces that we had earlier. First off, is it an LDF between two nonpolar molecules? Okay. Is it a dipole-dipole, meaning between two polar molecules? Is it a hydrogen bond? Okay. Or does it fit into one of our other categories, meaning is it an ion-induced dipole? Do we have an ion interacting with a polar molecule? Is it an ion dipole? Is it an ion-induced dipole where we have an ion interacting with a nonpolar molecule? Or is it a dipole-induced dipole, meaning we have a polar molecule interacting with a nonpolar molecule? Well, it's going to be this guy right here, which, if we remember, is not that much stronger than a LDF. So what does that mean? Let's go back and look at our numbers here. Okay, we know it's going to be a negative delta H. Okay, and I'm going to say it's going to be a fairly small negative delta H. And again, remember, these are kind of relative. We're not actually working with real numbers here, which does make this a little bit abstract, but we're just kind of getting a basic inkling of what's going on here. Okay, and again, we're going to call these dipole-induced dipole. Okay, so small negative delta H. So what does that mean? Well, if I add these three numbers together, what are we going to be left with? Okay, and again, I know these aren't real numbers, and that can be really, really frustrating to your level of student, because you want real numbers. You want tangibility in terms of actually being able to do calculations, but we don't have real numbers, so you have to kind of bear with me here. So we have a small positive and a small negative. I'm going to say these two cancel each other out for the most part. And granted, there could be one that's a little bit larger than the other, but for the most part, we're going to say they're canceled out, which means what we're left with is this large positive delta H, which means our delta H of solution, which are these three numbers put together. So we have delta H1 plus delta H2 plus delta H3 is going to result in a fairly large or larger positive delta H. Okay, which, if we remember back when we talked about our delta G, here, hold on, let me throw that over there. What that's going to result in, delta G equals delta H minus T delta S, a large positive delta S plus a negative over here. Okay, chances are, and again, this will make more sense as we go through it, but just kind of take me at my word here, delta H is going to be larger than T delta S. What that means is delta G is probably going to be positive, and that means no solution will occur. Therefore, it is non-spontaneous. Now, the fun thing is, if any of you cook, if you were to add oil and water and cook it up, or heat it up, guess what happens? They end up being able to dissolve in each other. Oil actually ends up being able to dissolve in the water. Well, why is that the case? Well, check out this statement right here. T is temperature, meaning if I increase my temperature, what that does is it increases the size of this T delta S statement, which means my negative can actually outweigh my positive, and therefore instead of a positive delta G, we can end up with a negative delta G, and therefore a spontaneous solution formation. All right, let's keep going. Let's look at a solution that we know will form. So we have sodium chloride and water, which we already know is a soluble solution, or a solution that will form. Okay, so let's look at step 1. And step 1 is going to be our sodium chloride. And remember, what's going to happen here is we are going to separate the sodium from the chlorine. This is our ionization process, if you remember that term. So this is forming the sodium ion and the chlorine ion. Okay, and this is breaking apart electrostatic forces. Okay, those electrostatic forces are fairly strong, very strong, and we're going to call this a positive large delta H. Okay, so we know it's going to be positive because we're breaking into molecular forces. It's going to be large because we are breaking electrostatic forces. And, of course, delta H just means our enthalpy. Okay, step 2 is our water. Okay, which, again, is going to be separating one water from another water. Okay, breaking this hydrogen bond and separating them so it has room to interact with the sodium and chlorine. Remember, these are our hydrogen bonds. Okay, so again, we're going to have a positive large delta H. Okay, last step, step 3. And this one's kind of interesting, kind of follow along here. These sodium ions are going to interact with water. These chlorine ions are also going to interact with water. So it's not just one ion interacting with water, it's 2 ions interacting with water, which means we almost have a multiple effect here. It's not just like if you dissolve sugar in water, you just have a sugar molecule interacting with water because sugar is not going to ionize. But in this case, we have the ionization process. So we end up with a sodium ion interacting with water, and we end up with a chlorine ion interacting with water. And it should be waterage because it's not just one interaction. The waters actually surround the ions, as we've already talked about. Okay, and this is going to form ion dipole forces, which are very strong as well. They're up towards the electrostatic. But because we're not just breaking one electrostatic here, we're basically forming 2 intermolecular forces for every one that's broken here. We're going to call this a very large negative delta H. Okay, so what does this mean? So let's go back up and talk about our equation. Delta G equals delta H minus T delta S. Okay, when you add these 3 together, chances are it's still going to be positive because you do have 2 larges and a negative that's very large. You're probably still going to end up with a positive delta H, but it's going to be a small delta H, a small positive delta H. Okay, from there, delta S is going to be negative, and it's actually going to be a fairly large delta S because remember, delta S is chaos, and we have a lot of chaos going on here with the ions separating from one species turning into 2 separate species. So the one species being sodium chloride, and then the 2 separate species being the sodium ion and the chlorine ion. So this ends up being a fairly large positive. Sorry, I think I just called that negative. A very large positive multiplied by this negative here. And that's going to give us a negative statement here that's fairly large, okay? And what that should do is cause delta G to be negative, okay? Basically, this negative statement should outweigh this positive statement, therefore giving us a negative delta G, or a spontaneous process, okay? So, what all does this mean? Okay, let's check this out. All right, so when we have a polar solvent, polar solute, okay, we know there's going to be an interaction here. What we end up with is the large positive and the very large negative in a lot of cases anyways. So we end up with a small positive, typically delta H, a solution, all 3 of these being added together, which should give us a negative delta G, therefore a solution forms. Nonpolar and polar solvent, because we end up with this large positive here and our negative only ends up being fairly small, we end up with a large positive delta H, which means no solution is able to form. And we can kind of continue that on. Small positive, small negative, ending up with a small positive. Therefore, a solution can form between 2 nonpolar solvents, like dissolves like. And then, of course, polar, nonpolar, same idea. Because of this large positive and the small negative, we end up with no solution being able to form because of that large positive delta H. Okay? So that's kind of solutions, looking at those steps and kind of understanding what's going on. Okay, we're going to stop here and we'll start the next video in just a moment. Thanks, guys.